every day, pieces of satellites fall back to Earth. Most burn up harmlessly in the atmosphere, but some survive with metal fragments crashing into farmland, forests, oceans, or even near cities. There are now tens of thousands of tracked objects larger than 10 centimeters in orbit, and the number is climbing fast as mega-constellations like Starlink continue to grow. Low Earth orbit has become a crowded, chaotic junkyard. On average, at least one sizable object re-enters Earth's atmosphere every day, and predicting exactly where uncontrolled debris will land is extremely difficult. So scientists have started looking downward to the ground beneath our feet. A team led by planetary seismologist Benjamin Fernando at Johns Hopkins University has pioneered the clever idea using seismometers, the same instruments that detect earthquakes, to track falling space debris. When a spacecraft plunges into the atmosphere at Mach 20 or faster, it generates powerful sonic booms. But here's the surprising part. Scientists aren't listening to the sound in the air. They're detecting how those shock waves shake the ground. Here's how that works. The sonic boom doesn't happen just once at impact. As the object races across the sky, it drags a continuous cone of shock waves behind it, like the wake of a boat, but in air. That shockwave cone intersects the ground far below, creating a moving line of pressure that sweeps across Earth's surface. Seismometers along that path feel tiny jolts as the boom passes overhead, while the object itself is still tens of kilometers up. By comparing the arrival times of those signals at many stations, scientists can reconstruct the object's trajectory, speed, breakup points, and likely debris field, almost like drawing its flight path from the ground. Fernando's team demonstrated this using the dramatic re-entry of a 1.5-ton orbital module from China's Shenzhou 15 mission over Southern California in April 2024. Using data from 127 seismometers, they mapped its descent and detected multiple mid-air breakups as it streaked between Santa Barbara and Las Vegas. Remarkably, their seismic reconstruction placed the likely debris zone tens of kilometers south of the official radar-based estimate. Because radar often loses accuracy at lower altitudes, seismic tracking may provide better information about where debris actually lands. This matters. Some space debris can contain toxic fuel residues or hazardous materials. Faster and more accurate landing estimates could help authorities narrow search areas, recover fragments quickly, and reduce environmental and safety risks. There are still challenges. Atmospheric winds, how efficiently shock waves couple into the ground, and gaps in global seismometer coverage can limit precision. And this method doesn't provide a long-term warning. It works best once a re-entry is already underway. But the potential is huge. The same system could help locate fresh meteorite falls, turning Earth seismic networks into planetary science tools. In a strange twist, the instrument we built to listen for tremors from deep inside our planet may now be our best way to monitor what falls from space. As our orbital junkyard grows, Earth itself is becoming a giant microphone listening to the sky come home. Thanks for watching. If you found this video helpful, give it a thumbs up and don't forget to subscribe to the channel.